Well, good afternoon, everyone. Welcome. My name's Ross Virginia. I'm a faculty member in the Environmental Studies program, and it's also my pleasure to direct the Institute of Arctic Studies here at Dartmouth. And a very special welcome. And as you can see, there's something else going on here. This is our very first video hookup with the Alaska IGERT programs at Fairbanks and Juneau. We hope we're hooked up with them. We can see them moving around. So anyway, our friends in Alaska, welcome. We're happy that you're here. And we hope we'll be doing this many more times in the future. So, fantastic. This is the first in the ongoing series of talks this year, sponsored by the Dickey Center in Arctic Studies and our IGERT NSF graduate training program in polar environmental change. And the series is titled Dialogues in Polar Science and Society. And if I know any of you open up a magazine and newspaper, what you see about science right now is about climate change. And a lot of what you hear about climate change relates to sea ice, melting glaciers, sea level rise, the really rapid and to some people alarming changes that we're seeing at both poles. So this series of talks and lectures throughout the year is to help us come together on the science, but also understand how the science links to the human dimensions of these problems. And so today I think we have a really special opportunity to begin with understanding some of the science behind the issues that are driving global interest in the poles. Today's speaker is Andrew Fountain, Professor Andrew Fountain from Portland State University. He's a professor of both geology and geography and chair of the geology department. Andrew's more than that to me. He's a very close colleague and friend. We've worked together close to 15 years now, I believe, studying the dynamics of Antarctic ecosystems in a place called the Dry Valleys. Andrew is internationally known for his work in glaciology. He's worked in Antarctica, Alaska, Sweden, where else?
I think that's good.
That's good? At least that many places. And so wherever it's cold and wherever there's lots of ice and wherever there are problems in understanding or lack of information about that ice, you can find Andrew. He studied the dynamics of the ice, the delivery and generation of meltwater, the chemistry of this meltwater. More recently, he's even interested in the life in the ice. He's branched into my ecosystem. He now looks at moisture in soils. And in all of this work, he takes a very interdisciplinary approach. He works with other scientists, teams of scientists, and he's always interested in the application of this science to solving real problems. In recognition for that, Andrew's served on the National Academy of Sciences Polar Research Board. He does a lot of work in outreach through the NSF Schoolyard program. So he does science, but he's very concerned about how this science is used and how it can solve real problems. Andrew's background, he did his undergraduate training in physics at St. Lawrence, a little to the north of here. And then he decided to move south for graduate study, and he actually started here at Dartmouth in geology at that time, I believe. I guess it was a little too far south because Andrew left and went to Fairbanks. Our friends in Fairbanks should be pleased by that, and completed his master's degree in atmospheric science there. From Fairbanks, slightly south, University of Washington, where he worked got his degree in PhD in civil engineering on areas around the geophysics of ice. If you go to Andrew's website, I encourage you to do that because that really shows the different types of work that he's been in, and he's got some really catchy images and a real library of information there. But in tracing his academic background, students often ask, like, how did you get to be where you are? And there's a really nice couple of sentences on his website that sort of describe this about Andrew. It says, my background in the subject started with ice crystals in the atmosphere. That's St. Lawrence and his interest in physics. Became grounded in lake ice, switched to sea ice, then I found a job in glaciers. I've remained there ever since. Well, we're all very happy that Andrew did find a home in glaciers and thank him for all the excellent work that he's done. And so today he's going to talk about just one aspect of the many projects he has running. And the title of his presentation today is The History of Glacier Discovery in the American West and Their Role in Global Sea Level Change. So how about a warm welcome for Andrew Fountain.
Well, thank you, Ross. I appreciate that. That kind of introduction makes my life sound a lot more organized than it really is. I kind of wandered around and did what could be done. And, like John Lennon said, life is what happens to you when you're making other plans. And that certainly is true for me. Is that Kathy Connor there in Alaska? Okay, it is Kathy. She and I have co-authored a proposal together, and I don't think we've ever met. So, so this is my digital meeting. So hi, Kathy. Okay, well, I'm very glad to be here, and thank you, Ross, for inviting me. This is always a pleasure to come to Dartmouth, and particularly with your Arctic legacy here. It's a real honor to be here and participate in this. So if we could have the slides. Okay, great, thank you. So what I wanted to talk about today is kind of where we came from in glacier studies, at least within the continental U.S. and U.S. science, and then how that might imply things and contribute to our current understanding about how glaciers contribute to sea level. The subject of glacier studies in the U.S. really began in September 11th, 1870. And this was kind of almost the end of one of the great USGS, or I should say U.S. Topographic Service geological surveys. And this is a picture of one of them. This is the King Survey. There's 4 great surveys. There is the King Survey, the Hayden Survey, the Wheeler Survey, and you probably heard of the Powell Survey. This is where Powell went down the Colorado River. But it was the first one, the King Survey, where he surveyed the 40th parallel that actually discovered glaciers, or at least was the first scientific recognition of glaciers being here, as our colleagues in Alaska would say, for the lower 48. And this is attributed to this guy here, Clarence King, who was in many ways a madman of his era, an incredible character, somebody that I'd love to meet. I would love to do an hour lecture on King alone. This is an incredible guy. He graduated from Yale under the tutorship of Dana's mineralogy, and during the early part of the Civil War in 1862, he rowed a boat basically from Fort Edwards, New York, up the Hudson, through Lake George, Lake Champlain into Canada. Then in 1863, while the war was raging, he kind of thought about it and decided not to go into the Union Army and went west instead and volunteered for the California Geological Survey and worked with Josiah Whitney, as in Mount Whitney, who was leading the expedition out there. So he volunteered for the California Geological Survey. And then once that was over, he talked Congress in 1867. He talked Congress into giving him $70,000 to mount a geologic expedition to the west. And he's 25 years old. Here we are at the end of the Civil War. Debt is all over the place in Washington, and he talks him out of this money, and he's named leader. He was the best guy to have at any conference. He was supposedly the wittiest man in the Century Club of New York City. And at the same time, he had a double life. He was known as James Todd over in the suburbs of Brooklyn, where he lived with an ex-slave and passed as a black man in Brooklyn and had this double. He wasn't married in New York City, but he passed as a porter, which allowed him to travel and be away from home for extended periods. That's when he was doing his geological surveys. Yet he came home and had a family of 5 children. And this is in the 1870s. So he's obviously an energetic guy to pull all this off. And this only came apparent after his death. Nobody knew this at the time. So anyway, it was Clarence King here who led this expedition across the West and eventually to Mount Shasta. And this is where his professor, Dana, actually did a lot of work in the 1840s. Dana was exploring the volcanoes. And so Clarence climbs the volcano on the west side, gets to the top and looks down and sees a glacier. Now, how does he know it's a glacier? Well, King has gotten around, he's been to Europe, he's seen glaciers, so when he saw this one, he said, I know what they look like. It's got ice, it's got snow, that's a glacier. And he gets the credit for it because he published this in the Atlantic Monthly in 1871. So the return time of publication back then was a lot faster. He discovers this in September 1870, and it's published in March 1871. So about 6 months later. And this, you can't see it very well, but this is King here. And Watkins, by the way, is a very famous photographer in the West. So while King is doing this, he has sent another party, Arnold Haig, up into Oregon to Mount Hood, and that's a picture of Mount Hood up there. So and Haig discovers the Sandy Glacier. That's pictured there actually. But it's interesting that Haig found the glacier about 2 weeks before King found his glacier on Mount Shasta. Who writes the report? The PI. Who gets to have his name finding the first glacier? King. So this is the way the system works. It's the PI who gets the grant, he gets the money, he directs the project, he gets his name first on the paper. So then also there's another party subsequently, Emmons, went up to, whoops, is that me? No, okay. Goes up to Mount Rainier, and there is the Emmons Glacier up on Rainier. So after that, it's one of these things that once something's discovered, then everybody kind of jumps in. And right after that report in 1871, you have Muir, you have Orisdale, rediscovered by the glacier up there, rediscovered by Pompelli and Hayden. So you have all these people now discovering glaciers. And Muir, this is a picture of Muir here. That's actually Muir himself, and that's on Mount Rainier. And this is an interesting story because what happens is Muir discovers glaciers in the Sierra. Now, how does Muir know it's a glacier? Because part of the problem is we're at the end of the Little Ice Age here. And the reason why they weren't discovered before is partly because, scientific interest really didn't migrate into the West until the 1840s. But also, there's a lot of snow. We're talking about the end of the Little Ice Age. So any of the glaciers that were there were probably snow covered, and the snow lasted well into the late summer. So they just didn't see much ice. So Muir, being an amateur, how does he know? He's never seen a glacier. So what he does is he puts a line of poles in the glacier across the width. And he sights along it to make sure that it's a straight line. And then he comes back a few days later, and lo and behold, that line has shifted. The stakes in the middle have displaced a little further downslope, and the ones on the side haven't. And he says, aha, this thing is moving, and this is a perennial piece of ice, a perennial snow cover, because I've seen it, it's been here for years, so this must be a glacier. So Muir does the science. That's how you define a glacier, perennial snow or ice that moves. So he writes this up, and this was published in the Overland Monthly, a Bret Harte publication. So this is the early science here back in the day. We're in these kind of broad publications. The Appalachian Mountain Club, for example, published a lot of this kind of stuff. So he publishes this, and then King takes him to task. You can still read this in one of the annual reports for the USGS, where King says something to the effect of, it's unfortunate that John Muir applies his abundant energies to such a fruitless task as finding glaciers in the Sierra. He should take these obvious talents and apply them to a more suitable endeavor. So here's the irony. King says, oh, there's a glacier, I've seen one, it's got to be a glacier. Muir does the science and gets vilified. So that's the importance of having a degree. If you have a degree, then people say, oh yeah, okay, fine. If you don't have a degree, then they kind of worry about you. And this is the Hayden survey. This is Ferdinand Hayden here. And then also, from my point of view, the way I kind of do this is I figure the first one to publish a report gets the credit. And Orsdale, for example, wasn't a scientist, but there was a newspaper account at the time when it's reported that he found this glacier. But it's interesting when you read this literature, once these glaciers are discovered, then everybody kind of gets in the game and says, well, I saw a glacier back in the 1850s when I was climbing such and such. And it's like, yeah, well, whatever, you know. You didn't say it back in the 1850s, you don't get credit. So let's see here. So this is the time of the original glacier discoveries, the Little Ice Age, and there were some other scientific reports that came out at this time. This is a guy from the USGS, Israel C. Russell. His initials, I.C. Russell. It's true, that's why people call him I.C. Russell, and he did a lot of original work in glaciers in the West. And back in the late 1800s, he's talking about the glaciers were slowly receding. So the scientific interest is now kind of building in this, where the USGS is taking an interest. And this is that area when, that time period when we're coming out of the Little Ice Age. Well, now in the 20s and the 30s, we're now really coming out of the Little Ice Age. Things are warming up rapidly. And Caroline here, Oliver Caroline, who was working with the Sierra Club, reported the alarming extent to which the glaciers are wasting away. So now they're observing this. So now this becomes the first episode of large public interest or great public interest in glacier recession. Because what happens at this time then, all these clubs, Sierra Club, the Mountaineers out of Seattle, the Mazamas out of Portland, the Obsidians out of Eugene, are now engaged in glacier research. They're the ones going out, making measurements, taking photographs, tracking these changes, and reporting them to the American Geophysical Union at the time. So very much amateurs were involved in this. And these are just some pictures of some of their efforts. Like, for example, here, 1937, the Mazamas, this hiking club, had hired an aircraft to do aerial photographic surveys of these mountains in Oregon. Here they made measurements. This is a displacement meter where, you know, they take a wire and put it in the glacier and then put the meter off on the bedrock, and then as the glacier flows, they can measure what the distance is, and they know what the speed is. So they were engaged in some fundamental research that then was reported then to the more scientific-oriented people in the Western U.S. So, in fact, just what about maybe 70 years? Yeah, 70 years later, just in 2007, the Mazamas, who continue to support alpine research, mostly in Oregon, funded another aerial flight to monitor or establish how much the glaciers have changed in Oregon. So you still have some legacies of these hiking clubs being involved in glacial research. And basically, the Mazamas are one of the few ones left that still do this. So now, during this period of recession, now between the culture that there's a lot of outdoor enthusiasm at this time, get out, go back to becoming a natural human, get outdoors. Combined with all the glaciers receding, there's great attention on the glaciers. And in Boulder, Colorado, for example, this is when they started annual glacier treks up to the Arapahoe Glacier. That went every year in July and only terminated in the 1960s when the Boulder water supply watershed stopped people from going into the watershed. But this was a legacy of the 1930s. And you can see here that Boulder was trying to capitalize on glaciers as scenic route to glacier regions. And if you know the area, this is no scenic route to glacier regions. It's a better place to get in the mountains, but that didn't stop Boulder from trying to make some money off it. Here we have a woman up on top of the Front Range here. This is near the Mills Glacier, and this is one of these trips. Here's some people that have climbed up on Mount Rainier looking into a crevasse. And it's very common to find a lot of these photographs that date to this period as people are getting more and more interested. So now the middle part of the graph here is, in this area, it's beginning to cool a little bit. And then during this period, this is the war years, so obviously there's not going to be a lot of attention paid to glaciers. But once you get out of the war years in the early 1960s and 1970s, there's this kind of period of time when the climate's cooling a little bit. And the glaciers are beginning to advance. And this is, and now this is the era when the scientists really take over, and more or less exclusively, it's the scientists that are tracking the glacier change. And here in this paper by Mark Meyer and Austin Post, talking about the relatively high percent of glaciers that seem to be advancing. And that's this period of time. That's also this period of time in the 70s that have been used more recently. We talked about this earlier today, where a lot of the climate skeptics think that the scientists thought another ice age was going to be forthcoming based on the climate cooling in the 70s. In fact, there's no weight to that report. It was just one of those things that kind of happened in the literature that were taken out of context. But that was the period of time that things were cooling a little bit. But of course, since then, we've now come out of that. It's warming much faster. And now again, we're in this era of paying attention to lots of glacier change, glacier retreat. And now, as we understand it, the impacts on global sea level. I want to show you a few pictures. I know you've probably seen these kind of things before, but this is the kind of thing that we've been using to estimate glacier change across the western U.S. So this is the Grinnell Glacier. And the perspective is a little bit different in that this is a little bedrock ledge here that's not in this photograph. So you got to look beyond. And this textured surface here are icebergs. So this is a lake that's formed as the glacier retreated, and this is all the ice that's breaking off the glacier. And if you have a good eye, you can see here and here how much the glacier's thinned, and in this area has disappeared. G.K. Gilbert, one of the great geomorphologists, USGS employee, great geomorphologist of the country, was in the area of the Sierra and took this first picture of the Darwin Glacier that Hassan Besejic has rephotographed. And you can see not only some retreat, but also a great amount of thinning. And just for scale, this boulder here on this moraine, this boulder is about 20 feet tall. So it's really changed quite a bit. And finally, the South Cascade Glacier has retreated out of this lake quite a bit. And if you have a good eye, if you have a good eye here along the sides, you can see that it's also thinned. This is one of my favorite photographs because I did my dissertation on this part of the glacier here, which is now gone. So that means I can't reproduce my dissertation. So it's like mine for the rest of my life, you know. You know, Ross says they can reproduce any time now, but you know, mine it's like, so I'm safe. And this is the question I like the least. And this is the one I get asked the most from our reporters is, well, when are glaciers going to disappear? And that's tough to answer. And partly this illustrates it. So you see I.C. Russell's picture of the Dana Glacier here on the left, and then Anderson's picture in 1940. And if you read the text here, it says, geologists believe that within 50 years, these ancient ice masses will disappear completely. Well, you know the punchline, right? They don't. It's still there. And that's because what happens is when a glacier is this small and retreats up into the cirque area, it's protected from melting somewhat by the shadowing here, right? So it's in this nice shadow. It gets a large fraction of its snow through avalanching. So it's going back into an environment that is very favorable for glaciers, that would not be as favorable if it was way out here, where it's getting direct snowfall. So to have a glacier really disappear really takes some doing. If we continue to have climate warming, this will happen, but it's just tough to make these things go away. So then you get in this whole thing, even among glaciologists. Oh, well, it's so small, it's not a glacier anymore. Well, you know, does it still move? You know, things like that. But it's not what we think of, kind of our popular conception of a glacier. It's just not very big anymore. So just to kind of give you a little geography of glaciers in the western U.S., we compiled an inventory of the entire U.S., and we find about 8,300 glaciers or perennial snowfields. We really can't tell the difference in the real small ones, but that's roughly what we have, and almost 700 square kilometers of ice. And that, just for your information, Washington has the most number of glaciers and the largest area of glacier cover, and Wyoming has a second largest area, but there's more little ice masses here in California. Does anybody know where that is? The one glacier in Nevada? Great Basin National Park. Good for you. Name of the glacier? Oh. Wheeler Glacier. Great, but if you had gotten both the park and the glacier name, you could have left. But now you had to get both of those. Yeah, but that's exactly right. And that's the last remaining glacier that isn't much bigger than the footprint of this building. So looking at the change based on the photographs that we've been able to find at the various national parks and other places, as well as aerial photographs, this is the kind of change that we're seeing. And all the glaciers are shrinking. The question is, some are shrinking faster than others. And frankly, we don't have a grasp on why all of these are changing this way, but we know a little bit about it. For example, these glaciers here, these very slowly changing glaciers, those are all the stratovolcanoes up there. That's Baker, Rainier, and Hood. So they stick so far up in the atmosphere, and they're getting so much snow at high elevation, it's buffering the melting at the bottom part of the glacier. And then we have this kind of transect from the ocean inland, and with rising temperatures in the interior faster than the ones near the coast, we're getting larger changes, we believe, and moisture deficit as the moisture doesn't quite make it that far. So there are some areas that we can get our hands around, but that's kind of our current project right now, is trying to figure out why these are retreating at different rates. And part of it has to do, of course, with the size of the glacier, its altitude distribution, and other topographic factors. Okay, so these are retreating. So there's kind of two main effects that we're seeing. This one's limited mostly to the northwest, at least in the U.S. This is Elliott Glacier on Mount Hood, and this is the margin of the ice here. It's really rock covered. So it's very hard to see unless you know what you're looking at. And the edifice of the volcano is fairly weak, so it discharges rock falls that cover the upper part of the glacier that gets incorporated in the ice, and then it melts out here and then covers the ice itself to several meters in thickness. Well, what has happened is that as the glacier retreats, it leaves these very steep moraines, steeper than the angle of repose, that are no longer buttressed by the ice. So the ice disappears. These really steep valley walls exist of incredibly weak material, just piled gravel essentially. And then if you get the right rainstorm and conditions, you have some of the valley walls fail. These walls fail. They get incorporated in the stream flow and then form lahars or debris flows. This is Route 35, just past Mount Hood Meadows, the ski area on Mount Hood, and this road was closed for weeks. This is another part of the mountain. This was from a different glacier on the mountain. This one was from Elliott Glacier that I showed you. This is the debris flow itself that crossed the roadway, and here they've excavated through it. So in Mount Rainier National Park, a couple of roads have been closed for over a year because of the same situation. So we have these hazards based on glacial retreat. But also, we have one of maybe the beneficial effect is we have more water coming into the streams. So, it's a storage problem. You have ice stored in the landscape versus ice stored or water stored in the oceans. So if it's on the landscape, what limits this melt is energy. So when does it melt most? When it's hot and when it's dry. So during the worst time of the summer or during the worst droughts, these guys are pumping out the most water. So it buffers the changes in the discharge of the streams, and therefore these streams are less susceptible to drought. And apparently a number of the towns and villages along the Silk Route in western China were founded and maintained on glacier-fed rivers because that was a constant supply of, or reliable, I should say, supply of water. Okay, so it helps the streams, but then the water's got to go someplace. And the water eventually ends up into the ocean. And that's what I want to talk about now, is this contribution to global sea level change. Iconic graph of sea level change and climate warming. Here we have the IPCC report of air temperature change with time and the resultant rise in sea level. And that little red line there is the laser altimetry measurements of sea level rise compared to physical measurements actually of the rise. So when you talk about sea level change, it's not just climate warming, but there's a whole host of factors that you have to take into account. You have the thermal expansion. So that's if you have a pot of water filled to the brim, if you put it on a stove and heat it up even slightly, the water will expand and flow over the sides. Same thing's happening in the globe. As the seawater warms up due to the air temperature increasing, it expands. Then you have the static component, which is the new water being added. That is, it's taken from the land and put into the ocean. And then you have local relative effects here. Coastal subsidence, which actually plays a large role, particularly where you have isostatic rebound due to the former presence of ice sheets, and so on and so forth. So a lot of these you have to take into account first before you can make reliable estimates of sea level change. This reservoir storage actually is fairly interesting. There's an article about a year ago saying that over the last 50 years, there would have been a lot more sea level rise if it wasn't for the fact that we have impounded so much water in reservoirs that it's backed off that rate of sea level rise. So that's actually a measurable effect. But today, I just want to focus on the contribution of ice to sea level change. So we're going to spend a moment on this graph because there's a tremendous amount of information in it. This is the rate of sea level rise. This is again reported in the IPCC report. And the red is thermal expansion of the water, and all the blue is ice contributions. Dark blue is from the glaciers and ice caps, small glaciers and ice caps, and then you have Antarctica and Greenland. And I'll first talk about the glaciers, and then we'll get into the two ice sheets. So the first bar here, this dashed line, that's the uncertainty about that estimate. And then there is the observed. So you notice the difference between the observed and the calculated is quite far apart. And the uncertainty of each of those values don't overlap very much. But since that time, since basically the 1990s, the difference between the estimate and the measurement is much closer. And the uncertainties now overlap. So we're getting better at this. So this is one take-home message. The other thing is obviously we're having a lot more thermal expansion and a lot more melt contribution from the small glaciers. Greenland is increasing quite a bit, and Antarctica a little bit. Okay, so here's the potential. If you melt all the glaciers and ice caps off the landscape, it ends up to be about a meter of sea level rise. If you melt Greenland, what's that, 11 meters? If you melt Antarctica entirely, it's 70 meters. So those are the big players in this, but there's no reason to suspect that Antarctica is going to be making any big, huge contributions of tens of meters anytime soon. And you can debate about Greenland, but right now the big player is small glaciers. There's not a lot of them, but they're melting a lot. Whereas the two big ice sheets, they're huge, but they're not melting quite as much. So that's what's going on right now. So when we talk about the small glaciers, in the melt of small glaciers, we tend to get focused just on the summer melt. Warmer summer air temperatures, more melt. Absolutely true. But the thing that you have to kind of also remember is what happens in the wintertime. So in the winter, you have snow accumulation. Summer, you have melt. And you add the two together, and that's glaciers either advance or recede or store or lose ice mass. In the winter, however, it's not just the amount of precipitation, it's the temperature. And we see significant changes in the west due to winter temperatures. So here's a NASA plot of northern hemispheric temperatures, and you can see that the winter temperatures over there on the far right are warming faster than the annual temperatures. So for areas, particularly in the northwest where I am, what happens is we're not having so much change in precipitation, we're having a change in phase of the precipitation. We're having more rain and less snow. That means less nourishment to the glacier. So you have less nourishment in the winter, warmer air temperatures, melting more in the summer, and the glaciers really get hammered. And this is a plot of Phil Motes of the trend in winter snowpack. And you can see from the red circles, larger the circle, the thinner the snowpack on April 1st. In the Sierra here, you're getting a little bit more snowfall because of the advection of moisture at higher elevations. So those guys are growing at least between 1950 and about 2002. But that's beginning to turn around. But the big message is that for most of the West, we're having shrinking snowpacks. Maybe this is, to you guys, kind of an academic interest, but for those of us in the West, this is where we get our water from. We don't really have the groundwater supplies or the surface water supplies as much as we have snow hanging up in the high elevations, and a lot of our reservoirs get water from snowpacks, and this is critical to us. So the effect of shrinking snowpacks can be seen here. This is South Cascade. This is that cooling period in the 60s and early 70s. And then of 76, 77 here, all of a sudden, the bottom falls out of the glacier. And this is a period of time when the circulation pattern shifted such that there was less advection of moisture in, but also a time when warmer air temperatures, winter air temperatures were sitting over the northwest, and the glacier just got hammered. It kind of slowed a little bit here, and now the bottom is just falling out of it again. So what is this kind of in a global level? Well, these two plots kind of show you the change in contribution of glaciers to global sea level in two different ways. This first one here is just the mass change per unit area on a glacier, and the second one over there is its contribution to sea level. So a little glacier could suffer the same amount of mass loss per unit area as a big glacier, but obviously the big glacier would make more contribution to sea level than a little one. So Patagonia is losing the most ice mass, but because it's a relatively small area, it doesn't contribute to sea level. So the work that we've been doing contributes to this darker green curve. But the big player are those glaciers in southeast Alaska, south central Alaska. The ice fields up there, the St. Elias Range, the Wrangell Range. These are melting so fast. This is of any one glaciated area in the world, other than the two ice sheets, this is making the biggest contribution. Your eye probably catches this dark blue. This is Europe, which is mostly Scandinavia. For a while, there was increased advection of moisture off the North Atlantic into Norway, and increased the snowpacks that not only buffered increased melting due to climate warming, but also then overwhelmed it such that they were advancing for a while. But since the middle 1990s, that's changed, and they too are now receding. So that's this contribution here for the small glaciers. Now let's take a look at Greenland here and what contributions that's making. Those of you who are part of the IGERT probably are aware of this, this graph here. This is the area of Greenland that's melting. So with time, there's been more area of the continent melting, implying more water is going into the ocean. And since the late 1990s, early 2000s, southern Greenland has experienced melt almost every year, and that wasn't the case in earlier times. So this guy melts a little bit at least every year now. Based on several different kinds of measurements, it looks like the mass of Greenland is shrinking. This is a great graph, although it might look a little obtuse. What this is the horizontal part is the time period over which the data is averaged. So you take a measurement here, you take a measurement here, you subtract the two, so then you say over this time period we've lost an average of whatever. And then the vertical bar is the uncertainty. So now this tells you a lot of information. It's the average period and the uncertainty. And it shows here that, that Greenland is beginning to lose a lot of mass. And this is based on modeling work. Some of those boxes are modeling. Some of those are through laser altimetry looking from space. And then some of those are gravity, using satellites that go over the ice sheet, and small perturbations in the orbit over time reflect changes in the mass of what's happening underneath, and in this case, that would be Greenland. So all these measurements, more or less, are showing the same kind of thing, that there's mass being lost from Greenland. And this is a big deal, because the more mass we lose from here, there's so much ice there that will accelerate the sea level rise. And this is Greenland's particularly important because, as you know, it sticks up there in the high northern latitudes, and with shrinking sea ice reflects a lot of energy back into the atmosphere and back into space because it's white. But as the sea ice begins to shrink, the darker waters absorb more solar radiation. Thinning snowpacks around the margin here reveal more land. They absorb more energy. So as the northern hemisphere warms up more rapidly, this guy here, Greenland, is going to begin to melt more rapidly. So you have this feedback, and that's one of the reasons why people are really concerned about the shrinking sea ice in the Arctic basin. Now, down in Antarctica, we're also seeing warming. Depending on how you look at it, maybe it's not so bad. First of all, the Arctic is warming twice as fast as this, maybe 3 times in areas. So this isn't warming as quickly. And although you see red and you think, oh my God, this is warming really fast, it's a danger zone, it's red, danger, Don't forget, this area here is like 40 below. So if the 40 below warms to minus 39 below, yeah, nothing's happened, right? So we're okay. But this is the signal maybe of warming. But what's happening out here is that when you hear about melting in Antarctica, you hear about this area, and that's because of the warm temperatures already there in the summertime are close to melting. Any further warming decreases the ice mass through melt here. So we're not seeing too much here yet, but out here, and this is what's been in the news, you hear a lot about melting. We'll get back to this because it's not quite that clear. And then also the oceans around it, these warmer colors indicate the warming of the oceans around the Antarctica, and that does become important. So again, through these satellites, through the satellite measurements, through these models, this shows the rate of mass change with time, and obviously it's not quite as clear. Yeah, you might say that there's a trend of mass loss here, but there's just so much uncertainty and everything that, yeah, it's probably there, but we need more robust measurements to kind of really pin this down. Except for this area right here. In the next 10 years, this, I predict, is what you'll be hearing about when it comes to mass loss from Antarctica. And I'll get back to that in a second. So, traditionally, this is how models, global atmospheric models, have treated the ice sheets. Because they're worried about all the air mass changes and everything. And then you have this passive ice sheet sitting there that if you increase the temperature, the ice sheet melts and the meltwater goes in the ocean. As far as that goes, that's okay. But here's how glaciers and ice sheets really work. That not only do you have melt, but then you also have the dynamics that actually flow more ice into the ocean as icebergs. And this is the part that is not included in the models. And this is turning out to be quite significant. And this was illustrated in the climate change report of the IPCC here, where they're basically saying that they don't know anything about the dynamical processes, and there is no consensus on their magnitude, which is saying, yeah, we know they're important, but we don't really have a handle on it, and we don't know what it is. This is where the science is right now, trying to figure out what the dynamical response of the ice sheets are, and that's tough. So here's Greenland, and Greenland just doesn't flow out everywhere. It flows out in little nozzles or little gateways, if you will, through different parts of the ice sheet. So when you try to model this kind of thing, you have this huge area with a large grid spacing, and then you have to make that grid spacing really small to account for all the little gateway exits of this ice sheet. So from a computational point of view, that's incredibly difficult. How do you do all that? So that's part A. And part B is, let's say you can do that. The problem is, at the base of the ice sheet, we don't really understand how ice sheets flow, or glaciers for that matter, flow over a substrate. We know there's a lot of friction, but how does that friction change with time? And what controls that friction? Because that's what controls how much ice gets into the ocean. And that's the other issue. So we have the oceans, we don't understand much about that, and we don't understand very much about the subglacial dynamics of the glaciers, and we don't have the computational methods to calculate that. That's the scary part. That's the part that concerns the scientists. They're working on it, but that's the big challenge. So here's one of these gateways. This is some work from Ian Howitt, and it's a little confusing here, but this is the ice sheet. It's flowing this way, and the front of the ice sheet was here in 1851, and now it's gone back, and here it is in 2001, now it's gone back. So the thing is as this little gateway, as the ice through this gateway retreats, what happens is you're losing friction or drag along the sides. So if you lose the friction, what happens? Things flow faster. And that's what this shows here. This is out at the mouth here, and this back here is up by the ice sheet itself. And you can't see the colors so much, but what happens is with time, as this ice tongue retreats, the rate at which the ice is flowing accelerates. And that's because of the reduction of the drag along the sides. So as these things move back, more ice is flowing out. This is the dynamical response that isn't well captured in the models at this time. And this is what the IPCC report was concerned with. Why is it retreating? It's not necessarily because of warming air temperatures, but in this case, it's because of warm currents. Here's the Imminger current around the southern part of Greenland, and this is a warm current that is melting the bottom part of the ice sheet where it flows out on, into the ocean. So through the melting of the bottom, the thing breaks up and the ice flows faster and you have more discharge. And this is a plot, color plot of the changing temperatures of that region. It's interesting that they have actually very good records of the temperature of these waters, mostly because of the tuna fishing, or excuse me, the cod fishing. If you know the temperature of the water and cod prefers certain temperatures, you can better estimate of where to deploy your fishing fleet. So now they have a fairly good record of sea temperatures, ocean temperatures, and they know something about the history of glacier change in the area, and they can estimate the effect, of the two. The problem is that ocean modeling is difficult to start with, and Dave Holland here, who did this work, was telling me that the models are pretty good, but the difference between a current flowing here and a current flowing there, off a few degrees, they can't distinguish. It's just, they don't have the accuracy of those models. And it's this kind of small deviation means whether this continent gets warmed by these waters or not. And that's, again, one of those uncertainties in this global problem that they're trying to deal with. You also have melting from the top. This also happens. This is a picture of the Ward Hunt ice shelf, and you can see all the water collecting here, and as the freezing level increases, the top part of the ice shelf melts and it breaks up. It breaks up through hydrofracturing, and that's what this shows. And that's what is going to happen here is that you have these fractures in the ice, water sitting on top. The water migrates or percolates into these fractures, and because water is denser than ice, it drives the water down. And because there's a fracture there in the first place, it's in tension, right? So now you have something in this crack driving it down, and it splits it open. And the ice shelf can then disintegrate. And this is the Larsen ice shelf here that completely disintegrated. This is in Antarctica here. This disintegrated in about 5 weeks' time. A ice shelf the size of Connecticut disintegrates in 5 weeks. It seems like everything in Antarctica is about the size of Connecticut when talking about icebergs. But anyway, this is another one of those Connecticut-sized things that disintegrate. And it goes into these small icebergs. Well, small, these small icebergs are about the size of Hanover, right? But, relatively speaking, all these icebergs flowing out into the ocean. And look at this picture, ready, there. See all the melt? That's all melt on the ice shelf that's ready to flow into these cracks and disintegrate the ice shelf. So this doesn't contribute to sea level because this is on a shelf. It's already floating out there. There's no contribution of new mass to the oceans. It's these glaciers now that are no longer buttressed by this ice shelf that they are now beginning to accelerate and discharge more ice into the ocean. It's not so bad here because the glaciers, there aren't that many glaciers. This isn't going to result in a catastrophic rise of sea level, but this could happen elsewhere on the continent. And this is one of the places. This is the place that you'll hear about within the next 10 years. This is the Pine Island Glacier. Nothing to do about an island. It's named after a boat. The boat's called the Pine Island. It's a Navy boat. And then they were there, and they described this glacier, so it's called the Pine Island Glacier. And you have this current around the margin of Antarctica here flowing in this direction. And if a tongue of this current flows over by the ice sheet, and that's one of these things, again, well, we can't predict this, but it might be happening, can melt the bottom of the ice shelf, and if this thins, then this part of the ice sheet begins to flow more quickly into the ocean. That's one of the triggers that we'll see in Antarctica. So right now, as far as these ice sheets are concerned, a lot has to do with the oceanography. And oceanography is incredibly expensive and incredibly complicated. But that's where a lot of the science is trying to couple our understanding of the oceans to the changes in the ice sheets. Now, this last thing is something you can witness yourself to some degree. When you fly to Europe, if you get a chance to fly to Europe, get a chance to a window seat on the left-hand side of the aircraft. And if you can see the ice sheet, if you have good weather, you'll see something like this. And this is a picture that I took outside of an aircraft. Of course, if you come back, if you sit on the right-hand side, you can do the same thing. But anyway, it's actually, I think they fly higher as you go towards Europe at a higher latitude. But anyway, so here you have cracks in the ice. These are crevasses. And this guy here is a lake. It's sitting on top of the ice sheet. And that's what it looks like when the snow's not there. It's this beautiful, beautiful blue lake sitting on the ice. These guys are dangerous. Because what happens is this water, like I just showed you for the ice shelves, this water can take advantage of crevasses and migrate very quickly into the ice sheet. It doesn't break up the ice sheet, but what it does do is it warms the ice. The ice in Greenland here is like 20 below or something, but once you put water in there, it raises the temperature up to melting. And then what happens is it softens the ice, so it allows the ice to flow faster, and also it can lubricate the bed of the ice such that the ice also flows faster. With climate warming, if the air just warms up and it's just conduction of heat from the surface to the bed, that takes thousands of years. We don't have to worry about it. But if this is water taking advantage of crevasses that hydrofractures to the bed, now you have a mechanism for rapid warming. Rapid warming and water flow at the bed, which accelerates the ice flow, which again ends up in increasing ice discharge to the oceans, raising sea level. That's the problem with this. And it's only been in the last few years, last 5 or 6 years, that we recognize that there's lots of cracks through ice that water can take advantage of. This was not really well known or even appreciated 10 years ago. And this is the kind of thing that they're watching with the satellites is this is the melt line here, kind of the edge between the snow and the ice. And as the melt zone retreats back to further and higher elevations, you have more lakes. These lakes drain into the glacier, warming up the ice. And Bob Hawley here is one of the guys that's looking into these kind of things. And this is some lakes there. So in a year's time, Bob, maybe you'll tell us the answer? He said yes. Okay. Late on a day, towards the end of a presentation, I like to show a table to kind of perk everybody up, you know. It's the sort of thing that, a little trick I learned in the trade. This is basically kind of two estimates of contributions from Greenland, Antarctica, and the small glaciers and ice caps. So basically there's kind of, and this is thermal expansion, and this is the 2100. So there's kind of two messages that I want you to get out of this. One is that the small glaciers are a player equal to the two ice sheets, at least through 2100. So we can't ignore those, because a lot of the emphasis in the media is on the ice sheets, and appropriately so. But you can't forget about the small glaciers and ice caps. The other message is that based on this estimate, a conservative estimate, we're looking at roughly 80 centimeters of sea level rise by 2100. This guy here of 2 meters, even the authors say, now this is extreme. Everything's got to be worked just right to get this much sea level. But it looks like now that the consensus is beginning to emerge around about a meter sea level rise by 2100. And what does that look like? That looks like this. This is based on some work by Jonathan Overpeck at the University of Arizona. And you can see the inundation along the east coast here. And there's similar maps in the west, but it's smaller because of, at least in the northwest, because of the subduction of the plates and the local rise of the landscape. But you can see large areas of inundation here due to 1 meter sea level rise, including some effects along the Hudson River here. Then you have the storm surges on top of this. So when you have a big storm, that raises sea level temporarily, and that goes inland much further. So this is going to be in our future for the next 80 to 90 years, it looks like. So these days are over. Bragging about 7 million tons of ice being lost due to energy production, this was humble, They can't be humble anymore if they brag about this much ice being lost, So they had to change their name. They went to Esso and then they went to Exxon, but it's the same company. And this is not really an indictment of the oil companies. I mean, they're reflecting cultural values, So we've changed a lot from this. So now we begin to realize that we have to be more careful about our energy usage and what our sources are and how we expend it. So, let me just say that it's hard to put an upending to this kind of presentation. And I haven't found a great joke yet to figure that out. But I will say this is that, in the past we have faced these kind of challenges and we've solved them, or at least mitigated them to some extent. And a great example is the ozone hole. We had good science and good policy together on an international level that has now resulted in the closing of the ozone hole. And whereas for a lot of this we can't stop, but we can stop it from getting worse. And that's kind of the challenge that we face now. So thank you very much.
Fantastic. We have time for a few questions. We're trying to record this, so please speak up if you have a question.
I was wondering, your work on the South Cascade Glacier, and then it's received out of the lake, how does the lake affect, like, if it's speeding up the process, because obviously it's touching the water, versus not being in the lake?
Oh, that's a great question. To the best of our understanding, and this is my thoughts on it. We haven't really done the study on it, but as the glacier retreats and a lake forms in front, you have extra mass loss due to the calving of ice into the lake. And there's a relationship between depth of water and the rate of ice calving off. So that's an additional mass loss that adds to melting basically of the glacier. So it appears, in my opinion, that the glacier has rapidly receded much faster than other glaciers in the area due to the presence of the lake and that extra mass loss due to the calving. So it's kind of one of those local effects that kind of reinforce maybe a larger climatic effect.
Meredith?
I'm sorry, this is going to be really detailed, but you showed the ocean modeling results from near Jakobshavn in the southwestern Greenland, and right before you show the track from Jason Fox or Ian Howitt where they show the margin. Has anybody compared those to see if there's actually like a lag or a one-to-one relationship of, I mean, it was a yearly ocean model prediction, right?
Yeah.
Have those been compared to see if that really is ocean temperature there? I mean, if you can see an influence?
Yeah, Dave Holland has done that. And he's actually done measurements in that fjord using special instruments that he's deployed from helicopters to look at exactly that kind of thing.
And is there a connection? I mean, do they see a real
Yeah,
direct?
yeah, David does, yeah, right, yeah. Not so detailed. Yeah.
Is it beyond the scope of your work to speculate on the effect of this on ocean currents, specifically the Gulf Stream?
Yeah, that's a good question, and I'll answer it a different way. I don't know much about the Gulf Stream, but certainly along coastal Alaska and in the Arctic, with all the influx of fresh water, it is changing certainly the salinity and nutrient content of those waters. And whether it's changing the direction and magnitude of the current, I'm not exactly sure, but it does have some effect. Yeah.
One of the things you showed was the deep water Antarctic, the water coming in underneath and starting to eat away. As that happens, isn't there also going to be a flux of water coming off the glaciers? It's also going to push, have an effect pushing that influx of warm water out as the melting occurs?
Well, there's kind of two issues interlinked there. One is there really won't be that much water coming off the ice sheet itself. It's too cold for that. And even if it did, that's a surface effect and wouldn't really affect these deep subsurface currents, which is several hundred meters underneath the surface. So they'd be decoupled anyway.
But if the melting is occurring underneath due to those currents coming in, aren't they going to be?
Oh,
the melting's occurring on the underside of the
yeah, you're right. So what'll happen is, as the ice melts, it creates fresh water compared to the salty water, and it'll just stay along the bottom face of the ice shelf. And through buoyancy, it will just stay on top. And if that became large, and I don't know if it would or not, but if that became large, that could be sort of helping to pull more water in, through some drag of the system. But I think that would be fairly small compared to the amount of heat and the flux of water coming in from the current. Yeah.
So in your history of the West, are there any women glaciologists? Any females that came up?
Yes, as a matter of fact. There's this woman who got her PhD at the University of Oregon in botany. And for some reason, I don't know, maybe Ross can explain it to me, but biologists seem to love glaciers. And she spent a career going to the Collier Glacier every year taking photographs. Ruth Hobson Keene. And we have this wonderful time series of pictures of this glacier. And she led a trip through the Obsidians, this hiking club, and others. And we have this wonderful record that we're using today to, or have used today, looking at the recession of that glacier. So she did this as, her main contributions were in botany, but she did this as a hobby. And we're finding it really useful.
One more. Mary.
Your records, your glacier records on the West Coast, you show a pretty big transition in the mid-'70s, right after 1975. And
Right.
there was, as you mentioned, I think, passing a huge change in PDO in '77.
Right.
So I've always wondered, is the glacier change that we're seeing a result of the change in the PDO, or is it global warming, or is the change in the PDO a result of global warming? And I was wondering if you could address that.
My understanding is they don't know. This is a Nate Mantua question. He's Mr. PDO. He's the one who invented that. But my understanding is it's either no or they don't know, because the atmosphere has patterns of circulation. And this was apparently a shift in that pattern that may not be a result of global warming. It just could be part of the PDO cycle. But let me amplify a little bit in that it just didn't affect glaciers, but there's this well-known paper by Ebensmeyer who looked at 26 different environmental indicators, including bird nesting habitat, salmon runs, mussels, and they all show the same, or should show, they do show a big shift right at that 76, 77.
So are the glaciers responding to that, or?
Yeah. I mean, that meaning the shift in circulation,
Yeah.
not the mussels.
No. But I mean, then it's not necessarily surface temperature warming. That I mean, global warming. But.
Right. Yeah. So that is a one of those contributing factors that in addition to global warming and warmer temperatures in the winter as well as the summer and this shift, the bottom falls out of this glacier. In the same way that the change in atmospheric circulation off North Atlantic in Norway did it the other way, you know, because the glaciers were advancing then because of all this increased advection of moisture into northern Norway. The glaciers were growing for a while until climate warming took over, and now they're beginning to recede again. So it can work both ways. In this case, it reinforced global warming in the Northwest and buffered global warming in the North Atlantic.
Well, as I mentioned, this was part of the series. This is the first talk in this Polar Sciences Society. So a week from today at the same time in Feinstein Auditorium, we have Richard Harris from National Public Radio. I think many of you hear his voice when your radio alarm clock goes off in the morning, but he's the science guy, right, that a lot of us hear about the changing world. And he'll be here and he's going to be talking about how the press sees this story. What do they learn from scientists? How do they report this? What's this other side of it? So Andrew was a fantastic introduction to the science of glaciers and sea level change, and thank you for finding. I worked with this guy for 10 years before he got me on a helicopter under his glacier in the Dry Valleys. But since then, I've been to Summit Greenland. I'm hooked. I'm all about the ice now.
Well, like I told some people before, it was a safety issue. I didn't want him to hurt himself.
Yeah.
It wasn't a turf issue.
Anyway, I passed the challenge. And you're all invited to Andrew's field site next year.
Absolutely.
Thank you, and all our